The oxidation of an alkene with osmium tetraoxide yields a syn diol, where both of the hydroxyl groups, these alcohols here, are facing the same side. That's what syn means, same. And the reason it is because of the mechanism that we're going to go through. So osmium tetraoxide is super toxic, so you don't see it used in learning labs. However, this is used in what's known as Upjohn oxidation, where you then use some N-methyl morpholine and oxide to regenerate this osmium tetraoxide catalyst. And then osmium catalysts are also used in the famous sharpless dihydroxylation. This is stereoselective dihydroxylation of syn diols. But for here, we're just going to go over the general mechanism and general reaction for what you should need to know for your exam. So like I said, this yields a syn diol, where we have both of them facing the same direction. Now, it's generally just shown as the osmium tetraoxide. There is technically a second step, as you're going to need to kick off this osmate ester. However, in most undergrad OChem 1 and 2, it's not really shown, or if it is, the mechanism isn't focused on. So we're not going to focus on that mechanism today. So first off, we have to draw our osmium tetraoxide. Now, we have it right here, and I'm sorry, my orbital geometry is not going to be perfect. We have this right here. Now what we have is cycloaddition to our alkene. I think it's 3 plus 2. And this is considered one step. Hexagon, and we have some of the electrons get kicked right back up to there. Now what we form, this is what's known as the osmate ester. And this is why it's syn. Because we are on this same face here. For osmate ester. And OS, duh. Now, this is generally it's focused on because we have that syn addition. Now, what the second step is, you'll usually have some sort of potassium or sodium bisulfate. Sometimes you have, depending on your professor, you're going to have hydroxide, or I'm not sorry, not hydroxide, peroxide, or sometimes they'll just say water because you're going to add water to kick off this osmate ester. And that's functionally all that does, is we're just going to kick it off to get to our syn diol. Now, remember, there's a 50-50 chance this adds from either directions. We could very well just put these on dash bonds, and we could have formed this instead, okay? These are not the same, because these would be enantiomers of each other. There's 50-50 chance. Now, you might be saying to yourself, well, aren't there other ways of doing dihydroxylation that is syn? You can think of potassium permanganate, and that's correct, because it'll form in a similar syn fashion, forming a manganate ester. However, potassium permanganate, if you don't have a alkaline solution or basic solution, or if there's heat added, you get oxidative cleavage of that alkene instead. Whereas with osmium tetraoxide, you don't get an oxidative cleavage, so it's much more tolerant, and it's more tolerant of other functional groups. Remember, potassium permanganate is going to oxidize alcohols. It's going to oxidize things to carboxylic acids. Potassium permanganate can oxidize benzoic carbons to benzoic acid. It's just going to mess with a lot of stuff. It's not very selective. Whereas our osmium tetraoxide is just going to mess with our alkene right here. And then if you're wondering about that N-methyl morpholine, and oxide, this is what it looks like. And this is what is used in that Upjohn oxidation, where you regenerate your osmium tetraoxide catalyst. Now, I'm not the best at, I gotta give this electrons, at organometallic oxidation cycles. So you're gonna have to look for an inorganic chemist there. But this is what you generally need to know just for basic organic chemistry. One, usually you don't see this organic chemistry too, is when you get to your alkene, you have osmium tetraoxide, that's giving you a syn diol, okay? Remember, syn, same face. Now, here we have free rotation. That's not that big a deal. These can rotate. But where this really comes into play is when we have a cyclic system where we don't have that free rotation. So let's imagine for a second we have something else. What are we thinking? We're thinking, all right, we have this right here. Okay, we have cyclohexene. These have to be on the same side. Okay. Now here, it doesn't matter because this has an internal plane of symmetry. That is a racemic mixture. Because if we were to flip this, these would also be acids. You don't have to worry about drawing the enantiomer as well. But remember, there's no free rotation, so these are locked. And this is where that syn dihydroxylation really becomes important. Again, now even when we don't have, let's go back for a second actually, for where we don't have a ring, we have that free rotation. What if we have a trans alkene versus a cis alkene? Well, again, we get something slightly different. So for the trans alkene, we're going to get the two different enantiomers. We're going to get one where it adds from the front face. In this case, we're coming this way. OH, OH. And then we're going to get the other enantiomer where it adds from the back. So you're going to get a racemic mixture. Now, for this cis one, because it's cis, it just adds one direction. Similar to our cyclic compounds, you simply get a meso compound. And I just realized I think I incorrectly called the cyclic compound a racemic compound. It is a meso compound because I'm treating my hydroxides, where we have that internal plane of symmetry. When we have that internal plane of symmetry, even though we have two chiral centers, it is overall an achiral molecule. It's known as meso. So I misspoke previously. So something like this is not a racemic mixture. It is a meso compound because we have that internal plane of symmetry. So remember, trans alkene gives us the racemic mixture of each, because we have 50-50 of each enantiomer. The cis alkene gives us that meso compound, that internal plane of symmetry. Same where we have a cyclic system, it's locked rotation. We have that meso molecule because we have that internal plane of symmetry. And if you want to get more organic chemistry learning, be sure to hit that follow button.